Good morning, students. Let us start the lab class. I was waiting for people to join, but till now only 7 students have joined. Anyway, we cannot wait anymore. There were some network issues also here. So let me start today's class. In the last few classes, we had seen in detail about the simulation of the inverter circuit and then the simulation of the NAND gate and NOR gate. So in today's class, let us see how to proceed with making the layout of the inverter. You will have to remember the inverter structure which I had discussed in the earlier class. In detail, I had shown you a 3-dimensional structure of the MOSFET. For today's class, you will have to recall whatever was discussed as far as the structure of the MOSFET was concerned, and along with that you may have to recall all the circuit related things also. So let us start with today's discussion. For preparing the layout of the inverter, all the other windows can be closed. Means you don't have to have your simulation window open or ADE window open. ADE stands for Analog Design Environment. That is not required because when we make a layout, we are not again verifying the functionality of the circuit diagram. Of course, after finishing the layout, again we can verify the functionality of the circuit diagram with respect to the initial circuit diagram also. That means when we simulate a circuit, we only have the SPICE model for the circuit. I hope you remember what is meant by SPICE. SPICE, simulation program with integrated circuit emphasis. So when you actually simulate the circuit diagram, it is basically the PMOS model, NMOS model, SPICE model. That is basically a mathematical model. And the model will have a symbol there, and the symbols are connected to for a circuit diagram. Actually, when you perform simulation, it is the models only are interconnected together. But when you perform the layout simulation, for example, let us say, then you have the physical transistor with all its area definitions, which means when we simulated the circuit diagram, we did not have the complete RC model or the complete physical model of the transistor. It was a mathematical model. Now, when we perform a layout, we actually will have a physical model which is going to be fabricated in the foundry. So once the layout is completed, then also you can perform simulation based on the physical parameters of the devices. Anyway, we will see that later. So for preparing the layout of the inverter, all the other windows can be closed. All the ADE window can be closed except for the Virtuoso console. So now in the Virtuoso console, Virtuoso is the tool which we are using for all analog designs. In the Virtuoso console, you can open the schematic of this particular inverter which you had simulated earlier. And then you can click on Launch and Layout Excel. You will have a pull down menu coming there. When you click on Launch, Launch Layout Excel, and the startup option, click on OK. Here you can see, I'll zoom this area. So you can see this startup option, layout create new or open existing is coming, and configuration automatic is coming. As we have not made any layout for the schematic, you'll have to, by default it will be selecting this create new only. So you can click on OK. Or else if you have done the layout in the earlier lab sessions, and if you want to open the existing layout, that is also possible here. Now when you click on OK, you have the inverter's circuit diagram at the background. Now when you click on OK, in the new file option, the tool selects the view as layout by default. You can click on OK. Now you can see here library, cell, view and type are there. Let me zoom. Library, We have kept it as design 2. Cell, inverter, view is layout. Earlier the view was schematic. Now the view is layout because we opened the tool called Layout Excel. Type is layout. And you have your default schematic diagram of the inverter. Now based on this, we can continue. The tool opens the LSW. LSW stands for Layer Selection Window and the Layout Suite. You can see here at the left side, you can see LSW, Layout Selection Window. And here you will see the inverter schematic. On top of this window, you will see a grid here now with 4 quadrants. You will see 4 quadrants, and each quadrant will have the grid that also you can see. Now let me discuss a little more about this layer selection window. Let me zoom. This is that LSW, where now you can see there are so many layers: N well, oxide, poly, N implant, P implant, contour, metal 1, via 1, metal 2, cap metal, via 2, metal 3, via 3, metal 4, via 4, metal 5, via 5, metal 6, then bond pad, then cyprot. I am not aware of what is this cyprot, and P substrate isolation. Then you have 2 texts, then you have PR boundary, again you have metal 1. So metal 1 pin you have, metal 1 drawing also you will have here. So you can see there are these many layers in the layer selection window. We are not going to use all the layers for our lab experiments. Whereas if you get into VLSI industry, there you will have to use all these layers almost for the new layout designs. So you can see, you will have to visualize the transistor now. If at all we have a inverter now, bottommost is the substrate. Above substrate you have well. Above well you will have diffusion. Here we don't call it as diffusion. Here we call it as implant. It is not diffusion process nowadays. It is ion implantation processes nowadays. In the earlier LSI processes, they used to call it as diffusion process, where they used to use dopants like boron and arsenic for P-type and N-type devices respectively, P-type and N-type regions respectively. Now because of the VLSI process, it is not actually diffusion, it is ion implantation, which is a much refined process when compared to diffusion. So you have this N imp and P imp. This N imp means N implantation, P implantation. So wherever N implantation is there, either arsenic or phosphorus is used as the dopant. Wherever P implant is there, boron is used as the dopant. Now you are seeing N implant. That means at the bottommost you have substrate, above which you have well, above which you have implantation, above implantation you will have oxide. So you can see this oxide also here. Above oxide you will have polysilicon. Polysilicon is the gate material. Above polysilicon you will have metal. Metal is for source and drain connections or for supply and ground connections. Now you can see in this window, metal 1 is there, metal 2 is there, up to metal 6 is there. What does it mean? It means that in the VLSI process, when we have so many devices on a chip, we cannot have connections only at the surface level, because these devices are packed. For example, in Bengaluru city, we have roads on the surface level wherever there are buildings. But at so many junctures or so many junctions where buildings are very tightly packed and there is a traffic issue there, then they either go for an underpass or they go for a overpass, flyover. And at times you can see that there will be a flyover, over flyover, over flyover. Now in Bengaluru we have metro trains also, we have other bypass roads also, and there are so many flyovers in Bengaluru city now. Many times it may happen that at the surface level you have a traffic signal, at the bottom, above which you will have a flyover, above which you will have one more flyover in the other direction, and it may go on like that. Now that is planned only to increase the traffic flow, or to decrease the traffic congestion, and to have better connectivity between the different parts of the city. Bengaluru is somewhat lesser number of flyovers when compared to Tokyo. In Tokyo, you will have again multiple flyovers over each other, because it is a very tightly packed city, and they can have 4 to 6 flyovers on top of each other, just to allow the flow of traffic in, let us say, in all 8 directions, not just in 4 directions, or even in the 4 directions for going to left side or right side or going straight. There are multiple options there. So that way, if all the ways are free, then there need not be any traffic signal at all, and everybody can move freely without waiting for the clearing of the other directions traffic. Same way in the VLSI process, when we have millions of transistors connected, it is not possible that only using one metal layer we will be able to connect all the devices. It may be possible, but we will have to have area for routing itself. We will have to reserve some portion of area only for routing. Routing means for connections. Always inside the chip also we make connections only using metal wires. These metal wires are not like cylindrical wires. Outside, now in the lab wherever I am sitting, there are a lot of fans and tube lights and projector and systems here, computer systems. Now all these are connected by means of copper wires, electrical wires, and all these wires are cylindrical wires. But in the case of an integrated circuit, inside the chip when you go, you cannot have a cylindrical wire because it is a planar surface. So there we have layers of metals. Just like dopants are implanted into the substrate, in the same way metal layers are also produced on the surface by means of a process called metallization. You will study more about all these processes in the theory classes, or you might have already studied in the theory classes. That I don't know whether the syllabus was yet to cover or it was already covered. I think it might have been already covered, because that comes in module 1 and module 2 itself. So please recall all those discussions of the theory class, where you have a process called metallization, and there are many procedures for metallization itself, such as sputtering or anodization, something like that. So by means of metallization, metal tracks are produced or created on the surface of the chip, and using these metals only all the devices are connected together. Whereas for gate connections, polysilicon is sufficient. For source and drain connections, they should have least resistance, because polysilicon also contains some amount of resistance. For gate connection, poly is alright, because there is no gate current at all for the MOSFETs. But whereas between source to drain, there is a current flow, for which we cannot use polysilicon. We will have to use a lesser conductive material. So we are using metal. In the older VLSI processes, they were using aluminum as the metal inside the chip, because it was easy to deposit aluminum. But in the present processes, they are using copper itself instead of aluminum. Just like we use copper wires outside for connections, now we are using copper wires even inside the chip for connections, because copper has better electrical properties when compared to aluminum. So now you can see metal 1, metal 2 up to metal 6. What does it mean? There is a flyover, over flyover, over flyover. Now in our physical city, in between two flyovers, it is simply a space there, or simply air blowing there. But what about inside the chip? Inside the chip, everything is solid material. So if it is one metal, above which one more metal layer is required for making connections, the gap in between the two metal layers cannot be left empty or free because it is completely silicon. It is completely solid crystalline structure. So the upper metal and the lower metal, they have to be isolated. If they are not isolated, then there can be crosstalk between two nearby conductors because we are dealing with nanometer dimensions. Please remember, we are dealing with the nanometer dimensions and micrometer dimensions. In future, we may move on to picometer dimensions. 2 weeks before, one of my old students invited me for his marriage, and that student belonged to 2010 pass out batch, almost 10 years before. He still remembers me that way. I think I'm lucky because hardly students will remember us once they finish their degree. Now, this particular batch of students, 2006 to 2010 batch of students, I had taken 4 theory classes for them right from 5th semester. 5th semester one course, 6th semester one course, 7th and 8th also one course each I had taken. So that particular batch of students had become very close to me. So many of those students are even today in touch with me, either in Facebook or through personal contact. Most of the time it is through Facebook only. So this student invited me for his marriage. I had gone there. I happened to meet his other classmates. And one particular student called Mujir Ahmad, who was in the BE class also with us, and he completed MTech also in our department only. But now our MTech branch is closed because of the lack of admissions. But that particular student, Mujir Ahmad, after finishing his MTech degree, he joined into Qualcomm. Now he is a design engineer in Qualcomm. So when I met him, I casually asked, what is going on now in the industry? He said, sir, we are working in 3 nanometer technology. I said, 3 nanometer? I had heard of 10 nanometer to 1 or 2 years before, where my students working at Intel had told me that they are working on 10 nanometer library. Now this Qualcomm ex-student, Mujir, tells me that they are working on 3 nanometer, characterizing the MOSFETs for the same. I asked which tool. Then he said, sir, we are using Cadence only. Cadence has developed the tool even for 3 nanometer. Then I said, okay, what next? I asked. Then they said, sir, later on it will be picometers. No. Earlier it was micrometers. We moved on to nanometer. Now later on in future, we are going to move to picometer. Now, once they reach 3 nanometer, naturally later on, they cannot say it is 0.1 nanometer or 0.2 nanometer. They will have to start with 100 picometer or 200 picometer. So maybe in future, maybe 10 years from now, we may be dealing with the switches. They may not be MOSFETs. I don't know what is going to come up in future. We may be dealing with the switches who will have dimensions in the picometers level. Still, I asked my student, my ex-student, I asked him, so if you people are dealing with the 3 nanometer, in future if it is picometer, are you really working with molecules or atoms, silicon atoms, or are you really working with electrons, individual electrons? Then he said, sir, we don't know. We keep on going down and we keep on finding out whether that dimension switching will happen or not. As long as switching is happening, we will transmit zeros and ones there, that's all. We really don't know whether it is the atom or electron or whichever way charge transfer is going on. That way, researcher will take care of it. So that is the idea. If we can make switches which are in the picometer range, then from VLSI to ULSI, ultra large scale integration, then to GSI, G and scale integration. That way it will go on. So here in this particular LSW, you can see only 6 metal layers. Whereas in the latest tools, there can be up to 12 metal layers, which means metal layer over metal layer over metal layer. Maybe in the next class, I will show you one of the PPT which I had prepared earlier, and I will show you a slide where how exactly these metal layers are formed. Right now, I don't have it in my laptop here. I am sitting in the lab here now. So in the next class, I will show you a particular slide. Okay. Now, to continue with my story of the lab class, because always the lab class is a big story for me. Unless I am sure that you have understood the concept, I will not have a inclination to continue further. That is why let me complete all these discussions Later on only you will be able to understand in what way we are going to make a layout. So you can see all these layers, metal 1 till metal 6 layers. What are these via then? Some people call it as via, some people call it as via. What is this via or via? This via is nothing but in between metal to metal, how will you make a connection? Now let us say you are staying in an apartment block, and if you have to move from ground floor to first floor, you have two options. One option is use the steps, one option is use the lift. Now ground floor to first floor you may go through steps. Ground floor to 10th floor, no one will use steps. You will wait for the lift. Now that lift is what? The lift is the one which is connecting multiple floors. In the same way, inside the chip here now, we have multiple floors. We have lowermost is substrate, above which we have well, above which we have implant, above which we have oxide, above which we have polysilicon, above which we have metal. Again in metal, we have metal 1 till metal 6 now. How do we connect these multiple layers? We will have to use via. This via is like that particular lift. Now this metal is made up of copper, whereas via is made up of tungsten. The reason is via has to be much stronger to have a physical support between two layers. Again, remember, we are dealing with nanometer dimensions. In the nanometer dimensions, even though the wafer is hardly 0.4 mm or 0.6 mm in size, the silicon wafer is less than 1 mm in thickness. Now in that less than 1 mm thickness, we are having multiple layers. All these layers are not even in millimeter dimension. They are in micrometer dimension. Transistors are in nanometer dimension. So the chip should have enough physical strength to handle all those layers. Now in between the two metal layers, we deposit tungsten, so that the tungsten is a stronger metal when compared to copper. But for connections, we use copper only. So that way all metal layers are copper, all vias are tungsten. You can again see via 2, via 3, via 4. There can be multiple vias to connect different metal layers with each other. Later on, I am going to discuss about the vias which we are going to use in our layout. So now, I hope I have discussed to some extent about the layer selection window. You don't have to worry about all other layers which we are not going to use. For example, bond pad, we are not going to use. Bond pad simply means that once the chip is complete, now from the chip, there must be a bonding wire connected for packaging. That means around the chip or adjacent to the chip in all four directions, we should have square bond pads there. Later on, once the chip is fabricated, once they make it a package, either in a ceramic or in a plastic package, the chip has to be connected to the pins which are outside the package. Between pins and the chip, there is either a gold wire or a platinum wire. That is called bonding wire. Maybe in the next class, I will show you the picture of an EEPROM, erasable programmable read-only memory, where the chip will be visible inside. Okay, I'll have to remember for the next lab class, I'll have to show you all those slides and the chips. Anyway, now that bonding wire is for connecting the chip to the external world by means of a packing. That packing can be silicon or plastic pack, ceramic or plastic packing. That packing is required because our fingers are big, whereas chip is so small. We cannot handle the chip through the bare fingers. That is why such packing needs to be done. After the packing, we either solder it to the PCB by means of the soldering lead, or using a hot air gun if the package is a BGA pack, if it is ball grid array pack. Using a hot air gun, the pack is bonded to the PCB. Otherwise, in your SIM card, there is no package at all. In your SIM card, the chip is directly packed inside a plastic connection with gold bonding there. That is why in your SIM card, you can see a surface that is gold plated, but the gold is very less there. It is gold plated to have very good connectivity. So in such a case, whenever packing is required along with ceramic or plastic package, then bond pads are required. In our case, we are not going to use the bond pad. PR boundary is going to be there. I am going to show you later on. Photoresist boundary that I am going to show you later on. So in this way, I have discussed to some extent the layer selection window. Now before going further, let me discuss one more important point. That important point is that above implantation, we have oxide layer. Again, oxide can be of two types, namely gate oxide and field oxide. It's also called as thin oxide and thick oxide. The thin oxide is the oxide that is meant for making the transistors, whereas the thick oxide or the field oxide is the isolation between the two metal layers. I had told you earlier, in between two metal layers, we need an isolation. That isolation is done by means of, again, oxidation, by means of silicon dioxide. So here, when we make a MOSFET, we have a channel below and we have a gate above. Now gate contact is by means of polysilicon. Below we need a channel to be induced. Now in between there is oxide layer. Now the point which I am trying to tell you is above oxide there is this polysilicon, which means whenever we have different masks, let us say we have a mask for implantation, we have a mask for well, and we have a mask for metallization or polysilicon deposition or in whichever way. Now this thin oxide mask and the polysilicon mask are one and the same that way, because oxide is below, polysilicon is above in case of a MOSFET. That polysilicon is the gate material contact, below which there will always be that gate oxide, without which the transistor will not function at all as a field effect transistor. So the point here is, we don't need an oxide mask separately. Once we make a polysilicon mask, that itself is going to work as a oxide mask. Such process is called as self-aligned process. Means the polysilicon mask itself is going to be aligning the oxide mask also. That way the polysilicon area is going to decide the oxide area in the transistor. So that is called self-aligned process. We are going to follow the same process here. Now with this introduction of layer selection window, let me proceed to the discussion of layout. If you have any questions, you can ask me now, or else I will proceed. Are there any questions? You can unmute and ask me if you want to ask. Okay, there are no questions. So let me proceed. You can see at the right side, there is this particular window which is having 4 quadrants. This is nothing like nothing but a graph sheet. So in the graph sheet, in general, we will make the layout always in the first quadrant, unless otherwise it is specified for other things. In our lab class, we always use the first quadrant. The reason is, once you make a layout, ultimately that layout has to be converted into a file called GDS2. GDS2 stands for 2 abbreviations. Generic data stream for information interchange. That is one abbreviation. One more abbreviation is graphic data system for information interchange. Just like you have ASCII code, ASCII, American Standard Code for Information Interchange, that we are using for all our computer communications. Whenever I type a key on the keyboard, each key will have a particular ASCII code allotted to it, and that binary signal itself is going to be communicated to the CPU from the keyboard. So in the same way here, when we make a layout is basically a graphical format. Now when it is a graphical format, whatever layout we make, when we send it to the foundry for manufacturing, we send it by means of a Gerber file. Just like in our normal computers working, we use zip files or RAR files, compressed files. In the same way, when these files, layout files, are sent to the manufacturer, they are sent by means of Gerber files. Now, these Gerber files specifically follow a format for the layout that is called GDSII. Sometimes people call it as GDS2. It is not actually GDS2. It is GDSII. Generic data stream for information interchange or graphic data system for information interchange. Both abbreviations are valid and both abbreviations almost mean the same. So why I am telling that is, whenever we have such layout file, ultimately it is going to be a database file which will contain graphical data, and graphical data will contain coordinates. Now when the coordinates are important, it is better that we use always the first quadrant here, because first quadrant, x-axis is plus, y-axis is plus. Whatever we do, it will be easy for the manufacturer to capture the data from the Gerber file or from the GDSII format. So we will be using the first quadrant only. Now whatever you see at the right side is called as layout suite. And when you maximize the layout suite, click on connectivity, generate all from source. The source here is our schematic file. We had a P MOSFET and N MOSFET, and we had connected VDD and ground and input and output. Now that particular schematic diagram is our source. Now we are telling to the tool itself that you make a connectivity, generate all that connectivity all from source, which means from the circuit diagram or the schematic diagram, let the tool capture all the connections, let the tool understand which one is metal, which one is polysilicon, which one is implantation, because the tool is intelligent. No, the tool is much more intelligent than we engineers also, because the tool is constructed by means of the expert engineers only or the expert Vlsi designers only. So from the schematic, the tool can easily understand that gate is polysilicon, source and drain are implantation, and all other connections can be metal. For source and drain, it can be metal. There can be pins, and pins can be again metal. Input pin and output pin can be metal. VDD and ground pins can be metal. All that will be understood by the Cadence tool itself. So we are telling to the tool, connectivity, generate all from source. Now a generate layout window will open with default attributes. You click on OK. It will show you all these things. You don't have to worry about all these things. Still, I'll zoom and I'll show you. Just for the sake of curiosity, I'll show you. I think you can see this now. So you can see this. When you click on generate connectivity, generate all from source, you can see generate IO pins, instances, extract connectivity, PR boundary. PR boundary stands for photoresist boundary. Please recall whatever was discussed in the theory class. There is something called photoresist, negative photoresist and positive photoresist. And each photoresist has its own advantage and limitation. Now this photoresist is the material used, just like a photography. Even in VLSI process, it is similar to photography, where a photoresist solution is used and multiple types of etching, and then again photoresist, again diffusion, implantation, metallization, again etching. There are multiple processes there. So here we have a PR boundary, photoresist boundary, means we are going to have a boundary for our layout beyond which we are not going to use at all. Now our layout suite is much bigger. All the four quadrants are much bigger. Our chip may not be so big. So why should we unnecessarily put a graphical data into that GDS2 format or into the Gerber file? So when we define this PR boundary, automatically the PR boundary will take care of the coordinates of the complete layout. That is called photoresist boundary. Now you can see by default all these tick marks are there. And IO pins create is there. Metal 1 is also there. By default, the layer metal we are going to use metal 1 only. We are not going to use other metal layers unless when we come to op amp, there we may ask you to observe the different metals, because there is a capacitor in op-amp. For that capacitor, there can be two metal layers connected. When it comes to the experiment, I'll tell you that. Now you can see ground, in, out, VDD. These are the terminal names. These themselves are the wire names or net names. All these are metal 1, metal 1. You can see ground, input, output and VDD. They are all now 4 metal pins. And by default, the tool has defined the width and the height, 0.3 mm and 0.3 mm. Now the pins cannot be in nanometer. Pins have to be in micrometer. Transistors are in nanometer now. Okay. Pins cannot be in nanometer. Why? These pins are going to be connected to the external world now through a bonding wire. So in that case, a nanometer VDD may not handle larger current at all. That is why VDD and ground wires cannot be in nanometer at all. So by default, it has chosen 0.3 micrometer and 0.3 micrometer width and height. And numbers are 1 each and create is true there. So this way, you don't have to really go through all these once again. Just for the sake of clarity, I am discussing this. Here you can see PR boundary shape is rectangle. And you can actually increase or reduce the size of the PR boundary. I'm going to show you later on. Aspect ratio is 1. So other things you don't have to worry. In fact, even I don't know all the details which are shown in this menu. What we simply do is, it is all part of the tools library itself. So we will simply click on OK. Once we click on OK, the PR boundary appears in our window. So press Shift F to see all the layers within the default layout. Hold the right click and move the mouse to zoom a selected portion. All that you can actually practice when you come back to college, and we hope it will happen soon. The color details are, orange border is N-well. You will have to remember these colors now. N-well is shown with orange, P diffusion is shown with red, P diffusion or P implantation. N diffusion or N implantation is shown with yellow, and in general diffusion is shown as green, polysilicon is shown in rose color, and contact cut is shown in yellow color, and metal 1 is shown in blue color. I'm going to show you now. See, this is the one. Let me zoom. I hope it is visible to you clearly now. Is it visible, or shall I open the Word file? I am using a PDF file. I think there's a slight resolution issue here. Tell me, is it visible? Is it all right? Or shall I open a Word file? Okay, let me open the Word file only. Okay, now I hope this is visible clearly. You can see this cyan colored window, which is there in the first quadrant. That cyan colored window is basically the PR boundary, photoresist boundary, which is created by default by the tool. Now you can increase the size to whatever size you want to increase. Now below you can see these 4 metal pins. Let me go down, let me zoom. I hope you can see these 4 metal pins now. These 4 metal pins are generated by the tool itself when we clicked on connectivity generate all from source. These 4 metal pins are input, output, VDD and ground. Then below that you can see the PMOS and NMOS. That means the tool has taken the PMOS default layout which is already present with the tools library. It contains both NMOS and PMOS default layout. So we are not going to make the layout of the devices as such. We are going to make the layout of the complete circuit of the inverter using the device's default layout. If you want, you can make a layout of the device on your own also. That is called completely full custom design. That is also possible. But here it is not required for us. Why? Because we are already using a 180 nanometer technology and we have already specified the device dimensions in terms of width and length. So by default, it is going to generate that layout. When you press Shift F, the color of PMOS and NMOS is going to change. That I'll show you here now. See, you can see here. When you press Shift F, you are seeing a color that is changed. Let me zoom further. Now I'll have to ask you some questions. So you can see a PMOS here. Now you can see a NMOS here, above which you can see those 4 pins. What we have to do is, we have to put all these things into the PR boundary now. Whatever is the PR boundary, the 2 devices will have to push into the PR boundary and all these pins will have to take up. In general, the tool will give you the devices and the pins in the 4th quadrant and it will put your PR boundary in the 1st quadrant. Now you will have to complete your layout in the 1st quadrant. Okay. Now look at this picture where you have a PMOS at the top, NMOS at the bottom. Now my question is, can you tell me the colors and for which color it is which layer? I want somebody to answer me either by unmuting or by putting in the chat box. Let us start with this PMOSFET only. The upper one is PMOSFET. The lower one is NMOSFET. I want you to tell me all these individual colors, they correspond to what layer? Because you are seeing a 2-dimensional drawing here. But basically it is a 3-dimensional layout of the device itself. It is basically 3-dimensional. Which one is the bottommost? Which one is the topmost? And can you identify the layers? That is my question. You can make an effort now at least. Later on, I am going to help you. I am going to discuss everything fully. But I want my students should interact with me to some extent. Otherwise, I feel as if I am talking only to a laptop. So, come on, my dear students. You will have to identify these layers.
One is polysilicon, I think.
Which one is polysilicon?
I think red or something.
In the
Red,
middle.
sir?
No, in the middle, see, there is this rose
Yeah,
color.
it's not clear. That thing is polysilicon.
Yeah. In the middle, exactly in the middle, there is a rose color layer. That is polysilicon. Below which there is oxide.
That color is not clear, sir.
Okay, color is slightly rose color. That let me zoom then. No, I have already reached 500% zoom. I cannot zoom further. So the color is fine, rose color. Later on, okay, Kuldeep has put
Yellow,
green.
sir.
Yeah, yellow is what?
implant, like
Which yellow? There are yellow squares here. See, there are 4 yellow squares at the left side, 4 yellow squares at the right side. What is this layer? Orange layer. Harshita has written orange is via. No, orange is not via.
mask.
Yeah, they are all masks actually. In fact, all these are masks. Actually, masks are not having any color. It is for our purpose that we have these colors. Otherwise, everything is silicon and metal. Actually, they are not having all these colors. For our purpose, for our design purpose, we should remember which layer is what. That is why these colors are given. Otherwise, the device is not colorful. Kuldeep has written green is diffusion. Green is a diffusion area. Okay, that is fine. That green boundary is a diffusion area inside which the implantation is going to happen. Any other answers?
Green is the active region. Similarly, yellow is P plus ka active region.
Where is yellow? Yellow is all these square boxes, right?
Yes, sir.
Yeah. These yellow are 4 squares. Harshita has written it correctly. Squares are contact masks. They are actually contact cuts. Contact cuts means at the top you will have metal, at the bottom you will have implant. In between them you want connections. As I mentioned about the tungsten, which is working like a wire, even when you have to connect a metal layer at the top, metal line at the top, to the bottom layer, that is implantation. Because source and drain are below. Source and drain connections are above. In such a case, when a metal has to be connected to diffusion, all these yellow colored contact cuts are used. So there are totally 8 contact cuts, 4 for the source, 4 for the drain. You can see that the device is completely geometrically symmetric, means whichever way you can take it as source or drain, it is immaterial now. Whether you consider the right side as the source or the left side as the source is immaterial. Only when you make connections, then whichever is connected to the VDD, in case of P MOSFET, that you will call it as source. Whichever is connected to the output pin, that you call it as drain. Otherwise, right now, they are physically identical. That way, right now, source and drain are interchangeable. After we make connections, then we define them as source and drain. So you can see whether the left side one you take it as source or right side one you take it as source is up to you. Now let us consider the left side one as source for P MOSFET. The reason is we will have to connect drain of P MOSFET to drain of N MOSFET. Then we will have to connect the source of N MOSFET to ground. Please recall the inverters connections. Drain of P MOSFET is connected to VDD. Sorry, source of P MOSFET is connected to VDD. Source of N MOSFET is connected to ground. Drain and drain are connected together and they are given as the output pin. Gate and gate are connected together and they are given as the input pin. Now you see that this rose color patch which is exactly at the middle in both of the devices, that is polysilicon. Below polysilicon, there is oxide. Oxide is not shown here. Why? Because it is a self-aligned process, as I mentioned earlier. Always below polysilicon, there is oxide, so there is no separate mask required. Now, what is this blue line? What is the blue line? We have this blue area. What is this blue area? Anybody?
Metal contact.
Yeah, blue area is metal. So for let me annotate here. Let me write this as source and this as drain for the P MOSFET. Now the source of P MOSFET has to be connected to VDD. Drain of P MOSFET has to be connected to N MOSFET drain. Let us say we take this as drain and this as source. Now the source of P MOSFET has to be connected to VDD. Drain and drain have to be connected together and they will come as output now. And gate and gate have to be connected together. That will be taken as input now. That way, I am crudely writing that. Later on, we will be using the exact layers for connection. So now, if source has to be connected to VDD, above you should have a VDD line. That line, you will connect it to this metal. VDD is also metal. Here in the MOSFET, that blue area is also metal. Now, below metal layer, you will see all these 4 contact cuts. Those 4 contact cuts are the tungsten pillars that are going down. Just like I gave an example of the lift between first floor to ground floor. Same way, from the metal layer, we are going down to touch the source area. That source area is implantation. That is why this green dotted line is indicating the total diffusion area or the implantation area. Now, around which you will see a red line. That red line is indicating that the MOSFET's complete area is defined there. It is simply shown as one at the top, one key at the top, one key at the bottom. That is only an indication that that is the exact P MOSFET's area. Now, what is this orange box which is around P MOSFET?
Is it that well, sir?
Huh?
Is it
Yeah,
that well?
exact. It is N well. Even Kuldeep has given the answer. This orange box around the P MOSFET is N well. Which means below you have a substrate, silicon substrate. Silicon substrate is basically P-type. Above which you will have a N well. Inside the N well, you have the P MOSFET now. Now this orange layer is N well, but inside in this N MOSFET, it is not there. Because N MOSFET is directly on the substrate itself. So is the P-type substrate indicated here in the diagram? For P-type substrate, what is the color here? No idea?
I didn't get your question, sir.
Okay, Kuldeep has given the answer as black. Brilliant. The question was, for P-type substrate, is there any color indicated here? Actually, the black screen itself is the P-type substrate here. Cadence is using the completely black screen. Both in schematic and in layout, they are using the black screen. In the black screen, they have these grids now. So this black color itself is indicating the P-type substrate. Okay. For a substrate, there is no separate color. We will have to visualize that in the bottom, at the bottom, we have the substrate, above which we have this N well. So naturally, N MOSFET has to be present in the P-type substrate itself. So for the N MOSFET, you can see a yellow color boundary here. That yellow color boundary, and here you can see a red color boundary. So for N MOSFET, why there is yellow color boundary? And for P MOSFET, why there is red color boundary? What does it indicate? I'll repeat the question. For the N MOSFET, there is a yellow colored boundary. For the P MOSFET, there is a red colored boundary. What does this indicate? Harshita has written formation of well. So formation of well is this orange color, right? This orange color is N well. That is for P MOSFET. I am asking about this red line. The red box for P MOSFET and yellow box for N MOSFET.
That red box is
Yeah. Tell me, vanilla.
No, I'm not confused in between, sir.
Fine. The red box indicates P-type implantation, yellow box indicates N-type implantation because the lower one is N MOSFET. So for N MOSFET, implantation area is defined here with the green color border dashed line. That green dashed line is indicating that it is the area where implantation has to be performed, where polysilicon itself is acting like a mask in between source and drain. So the area is prescribed for the implantation. But which type of implantation? N-type or P-type? So that way, for N MOSFET, it is arsenic or phosphorus implantation. That is shown as yellow color. And for P MOSFET, it is boron or gallium implantation. That is shown with the red color. This is how this whole thing is now having a GDSII data. Graphic data system for information interchange. Means by means of the color, the manufacturer will understand orange color is N well and red box is boron diffusion, yellow box is arsenic diffusion, and the green dashed line is the area which is meant for diffusion or implantation, and the contact cuts are there, metal wires are there, and polysilicon is there. That way, all the layers have the descriptions of the color. And for each color, there will be a different mask. In fact, the device will not become this colorful. Device will be actually a shining color, silicon crystalline structure. But these colors are meant for we designers, and it is meant for the manufacturer to understand about the layer selection. I hope that is clear. So with that, I have completed the discussion of the layers and the colors. Let us proceed with the connections now. If there are any other questions, you can ask me, or else I will continue with the further discussion. Okay, now see, the PR boundary is enlarged. That is easy. Once you come to the actual lab experiment to conduct here, we will tell you how to expand the PR boundary. Once the PR boundary is made larger, PR boundary stands for photoresist boundary. Now, inside the PR boundary, place these two devices, PMOS at the top, NMOS at the bottom. Why? Because we have written the schematic with PMOS at the top, NMOS at the bottom. So, it is better that we follow the same style that we followed using schematic. Otherwise, you can keep this horizontal also, you can make connections also. That is also fine. Because layout is an art, layout is a style. Just like people draw rangoli, that rangoli is an art, rangoli is also a personal style. In the same way, making layouts is basically an art. It is an engineering art, I can say, or I can say it is an electronics engineering art, because other artists do not do this except for electronics engineers. Of course, even computer science engineers are also trained for Vlsi design nowadays. In fact, my younger brother, he finished his BE in computer science, then he studied MS at Manipal University in Vlsi design, and now even though his basic degree is computer science, now he is a full-time project manager for Vlsi design at Texas Instruments, here only in Bengaluru. So I sometimes used to have a fun with him, and I used to say, I became electronics engineer and I became a telecom engineer, then a teacher. You became a computer science engineer and you turned out to be a Vlsi designer. That way, even computer science engineers are trained for layouts. In fact, a company called Sankalp Semiconductors is training the non-engineers also for such physical design. They are training even the BSc graduates for this physical design. The reason is, electronics engineers may demand a much larger salary for particular work, whereas BSc people will work for a lesser salary. So that way, company can save a lot of money in terms of the overheads. Work is going to be the same. But the work which is done by the BSc engineer, BSc person can be always verified by a electronics engineer or by a computer science engineer. But for connecting all these layers, seriously, high level of technical knowledge is not required. If he understands that which color corresponds to what type of layer, then that is enough. Only thing is, even a BSc person should understand schematic diagram and a layout. Now, this particular domain of VLSI design is called physical design. Physical design means taking a schematic diagram, you will have to prepare a layout. That is called physical design, where devices are physically present. Now you may see that there are only two devices, only one NMOS and PMOS. What about if we have 20 devices? When you design a two-stage operational amplifier, op-amp can have 10 devices. Now some big analog circuits can have 20 devices, 30 devices. Digital is anyhow, by means of synthesis, it is automated. Even in digital also, VLSI physical design is there later on, but it is mostly automated. That is why in digital design, people write Verilog code, then they synthesize it. Then the tool takes care of the physical design or the layout. Whereas in analog design, it's a custom design, where you only have to place each and every device. You only have to make all connections, because analog designs are much complicated. They are subjected to a lot of noise and bandwidth related issues. So that way, right now when you have only two devices, it is very easy to connect all of that. What about when you have 20 devices? We ourselves may get confused about which one to connect where. There, a careful analysis or careful design is required. So that way, making a layout is an art also, and making a layout is a personal style also. People, when they enjoy whatever they are doing, they will do very good designs later on. In fact, when people make a layout for a bigger circuit, they can patent it. And after patent it, that bigger layout itself, they can characterize for a given technology, such as 90 or 45 nanometer, or even for a 3 nanometer. Now they can sell it to Cadence itself. Now Cadence will store it in its library as a standard cell. That is how, using standard cells, people are making layouts, because somebody would have taken a bigger effort to make a standard cell. For example, let us say you make a standard cell for a 16-bit multiplier or a 16-bit adder for a given technology, let us say for 10 nanometer. Now you can patent it, you can sell it to Intel also. Intel will use it in his design, taking your standard cell. And you will get lifelong royalty for your designs. That way, even in VLSI design, if people take it with a lot of interest and people get into the core industry, then the core engineers in the electronics domain can earn more money than the IT engineers also. But it requires the knowledge of the fundamentals and a passion to work with the technology. That is what is required very much there. So that way, let me stop my philosophical discussion. Let me continue my lab discussion only. So you can see we have brought both these devices into the PR boundary. Now our job is what? Make a VDD line, make a ground line, and connect these two drains, and connect the source to VDD and source of NMOS to ground, connect polysilicon together and join them, and take all those 4 pins. You have these 4 pins, VDD, ground, input and output. Bring those 4 pins again here and connect them accordingly. That's all. That is going to be your inverter layout. So there are some discussions here. After placing the devices, zoom the space in between the transistors. In the LSW, select poly. Remember LSW, layer selection window. There you select poly. Now in the layout suite, press P. P for path. Press P. Now place the mouse at the middle of the gate's lower contact of PMOS device and click once. P is for path in the layout suite. Release the finger and move the mouse downwards. I am happy in reading my own sentences, which I wrote 10 years before. In fact, this lab manual was prepared by me long back. Even the snapshots I had personally taken and put. I had a passionate work with the Cadence tool at that time. And I had two colleagues, one colleague called Savita Patil, one colleague called Pavitra. Both had industrial experience. Savita Patil had an experience with the digital domain. Pavitra had the experience with the analog domain. So I had taken their help a lot. Even now, whenever I remember them, I thank them mentally at least. Because through their help, I could make this manual 10 years before. Of course, the procedure remains the same anywhere. P is for path in the layout suite. Release the finger and move the mouse downwards. The poly path will move along with the mouse. Move the mouse until the gate area of the NMOS device gets overlapped. Bring the cursor exactly to the middle of the path and double click. The poly path between the gates gets realized. The area can be zoomed further and the devices can be moved for the exact overlapping of the poly layers. I'll show you that here now. See, this is the one. You'll have to bring these two devices exactly at the center this way. Then you'll have to use all those procedures of pressing P and bringing a poly path, because we are connecting poly to poly. When you are connecting poly to poly, gate to gate connection. So now you can see there's a slight overlap here. You can see this. See in the P MOSFET. Now you can see, right? You can see that PMOS gate is here, whereas the poly path is slightly offset. This is an error. This is an overlap error. When you perform the testing of this layout, the tool will give you an error message, because this is not advised. Why? Poly path is slightly offset. Remember, we are dealing with nanometer dimensions. So it should be correctly overlapping there. If there's a slight shift there, what is happening? Below polysilicon, we have oxide by default, right? Now, oxide and poly will not have a correct overlap here at this particular area. That will lead to an error. That is why now you will have to move the device slightly to the right side. Move the PMOS device slightly to the right side so that the path will exactly overlap. When the path exactly overlap, you can see in the N MOSFET, it is exactly connected, right? See, in the N MOSFET, it is exactly connected. But in the P MOSFET, there is a slight offset. This should be corrected. Otherwise, this is an error. Until this error is resolved, the tool will not proceed further for the further verification. That is why I told layout is an art, layout is a personal style. Where was I? Let me zoom out now. Fine. This way we make connections to the gate. Later on you can see. Again, further I'll zoom. It is now 9:35. I'll be concluding in the next 5 to 10 minutes. Okay, you can see here now, poly is connected here, right? Gate and gate are connected. Next, you can see drain and drain are connected by means of a metal wire. Procedure is same. Press P and select a metal one there and make a path here. So drain are connected. At the top, we make one more metal path for VDD and we connect the source of PMOSFET to VDD. Again, we make one more metal path for ground and we make one metal connection from the source of NMOSFET to ground. Then we have this metal connected. We make one more metal path here and place the pins here. You can see these 4 pins. Whenever you click on this particular pin, the tool will show you which pin it is. Now in this window, you can see all 4 pins are simply blue squares. But when you click on this, it will become pink in color and you can always press Q. When you press Q, it will show the property window. In the property window, you can identify which pin it is. Correspondingly, that particular pin, bring it here and place it on top of this. VDD place on this. Ground place on this. and output place somewhere here, connect a metal wire, input place somewhere here and connect it to gate. That I am going to show you now. See, here drain and drain are connected of PMOS and MOS and the output pin is kept here. You can see this. Similarly, poly gate are connected and this is coming here. But now the input is metal, but connection is poly. What to do now? Input is metal. Metal is at the top layer. Connection is poly. Poly is at the lower layer. How to connect them together? This is where we need one wire. We need a tungsten wire in between. So we take a wire now. That wire will be metal to poly. Metal 1 to poly. That wire again we take from the layer selection window and we place the wire there. When we place the wire there, it indicates that metal and poly are connected by means of a wire. That I'll show you here. See, there is this option of wire definition, M1 to poly 1, metal 1 to poly 1. You select that, simply click on hide, then come back here and place that wire. See, let me zoom. Now you can see this wire here. Gate are connected by means of a poly wire and there is a metal wire. You can see a wire. The wire by default contains a contact area. Let me zoom further. It is already 500%. Okay. You can see a blue square there. The blue square is metal at the top. You can see a yellow square inside. That yellow square is a contact area between metal and poly. You can see a poly area there which is at the lower level. Poly is at the lower level, metal is at the upper level, yellow square is in between. Please remember, always whenever we make such connections, there will be a overlap around. Not overlap, extended area. There is an extended area around because that is what is the complication of mask. We have to clearly define which is the contact area. We have to give some tolerant space around the contact area for a metal. So metal has to be bigger than the contact area. Otherwise, sometimes if the mask slightly shifts this side or that side, left or right side or up or down side, now the area may be lost for connection itself. Those are called layout errors. If such errors occur, physically such connections may not happen properly when the chip is manufactured. That is why there is an additional area beyond the contact area. Metal area. Again, additional area for a polysilicon also. This way we place a wire. Wire will always contain now 3 layers. That M1 to poly 1 wire will contain 3 layers now. That is polysilicon below, in between it is tungsten and above which it is metal. So this is how we place wire. Now the connections are done. Output connection and input connections are done. And you can see the ground connection is also done. See, ground is here and VDD is here. We have kept the VDD pin here and the ground pin here. What is this one now? This one is P MOSFET is in N well. Now the body of P MOSFET is N well. When the body of P MOSFET is N well, the body of P MOSFET must be connected to VDD, right? To avoid leakage current within the substrate or within the body, that particular junction which was inadvertently became a PN junction, that PN junction should be reverse biased. We did not produce a PN junction on our own. It was produced because of our processes. So when you look at a N-well process, you will see so many parasitic diodes there. Between a substrate and a well, you have a PN junction because substrate is P-type and well is N-type. You will have a PN junction there. That is a diode. We did not want a diode there, but because of our own process, diode was formed. That diode should never conduct. as that diode should never conduct, even for leakage current also it should not conduct. So what we do? We reverse bias the diode by connecting it to VDD now in case of P MOSFET. So N region is connected to VDD so that the PN diode which is between substrate and well, that remains reverse biased. So you can see this is also a via. What type of via? N well to P sub via. N well to P substrate via, where you can see N well orange color. You can see yellow color N diffusion, right? Yellow color stands for N diffusion. And this red color stood for P diffusion, which I had discussed earlier. Again, in that N diffusion, now you have a diffusion area or implantation area, that is green color. And above you have metal. In between them, you have a contact area. You will have to visualize how many layers here now. P substrate, below, N well, above. P substrate is anyhow black color, N well above, and that has to be connected to VDD now. N well has to be connected to VDD. So if N well is connected to VDD, there the implantation is what? N type. See? Now that implantation is again connected to a contact cut, that is tungsten, and tungsten is connected to metal at the top. Metal is connected to VDD. So that way you will have to visualize these connections. Now what is this at the bottom now? Can anybody tell me what is this at the bottom? Kuldeep, very good. It is P substrate contact. Now, N MOSFET is residing in P substrate. Now again, there is a PN diode, right? Between this N-type implantation and the P-type substrate, there is a PN diode. That diode has to be reverse biased now. There should not be a leakage current in the body of the N MOSFET. So for that purpose, even this body of the N MOSFET is substrate itself, P substrate itself. That should be connected to ground. Now look at this red box. That red box indicates P-type implantation, right? Because substrate is P-type. It's P-type implantation. And inside you will see a implantation area. That green area is implantation area. And inside you will see a yellow color contact cut. That yellow color contact cut is tungsten. The tungsten is connected to upper level metal. And metal is connected to ground here. Now, even though we write ground at the bottom and VDD at the top, when we write schematic diagram, when we actually make a layout, ground and VDD are both at the top side. Please visualize that. Ground and VDD both are at the top side now. I'll zoom out to show you the complete picture. It keeps going down. Wait a minute. Again, I'll have to zoom in. Let me make it around 300%. Layout is an art. Teaching is also an art. Learning is also an art. We should have enough patience. Let me further reduce it because I want you to see the complete picture now. Right. So you see here, now this is the completed layout. In the completed layout, PMOS body is connected to VDD. NMOS body is connected to ground here. Why we did not put a via here like this? It is not required. Why? NMOS is already in P substrate. The black area itself is P substrate. So whether you put it here, whether bring it somewhere here and connect one more metal layer, that doesn't matter. Now it is very nearer to n MOSFET itself, that is enough. Otherwise, if you want to be specific, just like you have a wire here, you can bring this wire to the top somewhere here and connect one more metal line here for your own satisfaction. Otherwise, this area is also very much nearer to n MOSFET, which means the body of the n MOSFET is connected to ground. Now, please visualize all the blue lines are at the top and the black layer is at the bottom. Black layer P substrate is at the bottom. Blue layer metal is at the top. In between, all other layers are there. So, even though in the circuit diagram when we write VDD at the top and ground at the bottom, as per our writing style or writing habit. Now in the layout, what it has become was, you may again think ground is at the bottom and supply is at the top. No, not that way. This blue layer is always the topmost layer. That means when you visualize this, you are seeing now the inverter's layout from the top. Always you will have to visualize now, you are seeing this layout from the top. It is a top view of the layout. From the top you go to the bottom, blue is at the top, then below you have polysilicon, that is rose, below which you will have implantation, below which you will have N-well, below which you will have P substrate. You will have to visualize that way. So here ground is not lower level, VDD is not upper level, both are at the upper level, but they are not connected. You can see here. Now you cannot cross over this metal with this metal anytime. Then there will be a ground and supply short. Anyway, I will be ending the class for now. In the next class, I will go in further detail about how to verify this layout. We have the verification called DRC and LVS and RCX. I will not discuss them now because, again, my habit is that whenever I discuss fully. Otherwise, I don't discuss. When I discuss fully, I don't want to hurry up with these things. I want to discuss everything in detail, at least for my own satisfaction. So, let me end the class for today. If you have any doubts or questions, you can remember till the next lab class. In the next lab session also, you can interact with me. In the next lab session, I will discuss about how to verify this layout using LVS, DRC and RCX. And later on, in the next lab class, let us discuss about how to make a layout for NAND gate and NOR gate also. Later on, we can actually pick up speed in our classes. We can go faster later on, once these things are fully understood by the students. So if there are no more questions, let me end the class.
Sir, in the observation book this time, should we write whatever is present in the lab manual, or like last time we should write something which is new?
Whatever you understood, you can write one page there. You can write the circuit diagram also, then you can write the layout diagram also on your own. Try to write this layout diagram on your own. Don't worry about colors. You don't have to use color pencils. Use monochrome only, and using monochrome regular pencil only, you can try to write the same layout. Only when you write it, you will understand it better. It need not be too much detail, but you can write all those squares and all those paths. That is enough.
Yeah, sir. So the circuit diagram and the layout
diagram. That is
a little
enough.
bit of what we understood.
Correct. That is enough.
Yeah, okay, sir. Thank you.
Okay. So Deepak, shall we end the class?
Sir, I have created the assignment work, sir, in classroom.
Okay. So Deepak has created the assignment work. Students, you post your observation page into that assignment work. So see you in the next week, in the next lab class. Take care and goodbye. Keep exercising and keep taking care of your health. Keep consuming Chavanaprasha daily morning before breakfast along with a little bit of ghee. That will always keep your blood pure and keep your lungs warm. As long as your lungs are warm, as long as your blood is pure, you are immune. Keep doing exercise so that the blood will keep getting circulated throughout your body. So, remain healthy, be happy. See you in the next lab class.
Thank you, sir.
Okay.